Okay, we have a problem here with a soccer ball. It is kicked at 22 meters per second at a 70-degree angle to the horizontal on a level field. How far away does it land? Okay, this is a projectile launched at an angle. I'll do a quick sketch. Here's the level field. Here's the soccer ball. It is kicked with an initial velocity, which I'll mark here with VI, and the angle to the horizontal, I'll put a horizontal reference line, is theta equals 70 degrees. Okay, and we are asked to find the horizontal displacement. Now, since they did not give us the velocity components, before we even set up horizontal and vertical UC charts, the first thing we have to do is find the vertical and horizontal components of the velocity of this ball. Okay, I'm going to start off by drawing them. I complete the right triangle where the VI is the hypotenuse. I'm going to draw in the legs here. And then since VI goes up and to the right, my components go up. This one's up and to the right. And I will label them VI vertical, and I use Y for that. And then the horizontal one is VI horizontal, and I use X for that. Okay, I'm going to calculate the components. VIX, the horizontal component, is VI times cosine of theta. Now I'll plug in the values, and I get the the initial velocity is 22 meters per second. That's VI. And cosine of 70 degrees. And that gives me a VIX of, let me get my calculator up here. I've got 22 times cosine of 70. 70 hit cosine, there's a cosine of 70. And I get an answer of 7.5. 7.5 meters per second. Okay, the vertical component, VIY, is VI times sine of theta. Plug in the values, 22 meters per second times sine of 70 degrees, and we'll calculate that. I have 22 times sine of 70, and that gives me an answer of 20.7 meters per second. Okay, so VIY is 20.7 meters per second. All right, I now have those components, and so I'm now ready to set up my horizontal and vertical UC charts. Okay, let's do that. The horizontal, I'm going to do on the left, and vertical over here on the right. Okay, I'm going to start with what I know about every projectile. Any projectile problem at all, I can put in the accelerations. The acceleration under horizontal is 0. And the acceleration under vertical is 9.8 meters per second squared, and I will put the direction of down. While I'm at it under vertical, I will cloud a code. I'm going to make down positive and up negative. There's my nice code there. All right. Next thing I'm going to put in here is the horizontal initial velocity, which I just calculated as a component there. That is 7.5 meters per second. And the vertical initial velocity, VI, is 20.7 meters per second, and that direction is up. I'm going to go back and refer to my original diagram just for confirmation. The horizontal velocity is to the right, and the vertical velocity is up. Okay. Now, they want me to calculate, let's go back and take a look here, how far away does it go on a horizontal field? So my unknown is D under horizontal. I don't have enough information under horizontal to calculate it, so I'm going to have to go over to vertical. And what I need to find out is how much time this thing is in the air. So I'm going to do that under vertical. And I'm going to find, first of all, the time it takes to get to the tippy top, the halfway point, where VF is equal to 0. And I'm going to put a note here that that is at the halfway or tippy top point. Okay, that's vertical VF 0 at the halfway point. It has just stopped going up. It's about to start coming down. So we now have enough to calculate T at the halfway point, so let's do that. I'm going to use the equation T is VF minus VI over A. That, by the way, is seafood from the equation on the reference table, which says VF equals VI plus AT. If I solve that for T, I get VF minus VI over A. All right, we're ready to put numbers in here. I've got a VF of 0, so I can arrow 0 that. And I have T is equal to negative VI, negative, and then for VI, I'm going to put in 20.7, but I have to use code. My code for up is negative, and so I'm going to put in negative 20.7 meters per second divided by my acceleration A of positive, because it's down, positive 9.8 meters per second squared. And I can now calculate that. Get my calculator back out here. Now on the top I have minus a negative, and so that's going to be positive 20.7 divided by positive 9.8. That's going to give me a positive amount of time, and it is 2.1 seconds. Oops, T is 2.1 seconds. Now that, I remind myself, is to the halfway point, or the tippy top. So if I go back to my original drawing, if I draw in the actual path taken by this projectile, and it's going to land over here, I've found the time to the tippy top is 2.1 seconds. I need the whole time that it takes to get to where it lands, and so the whole time is 2 times 2.1 seconds, and that is equal to 4.2 seconds. Okay, so now I'm ready to work on the horizontal side. The time, of course, doesn't have direction, so that goes under either up chart, so I can add that. 4.2 seconds, and that is the whole way. And that's what I want, because they asked me how far away from where I kick the ball does it land. So I'm now ready to calculate horizontal displacement. D equals VIT plus 1/2 AT squared, making use of the fact that I know A, VI, and T, and that's what appears in this formula. Okay, I know that A is equal to 0, so this whole second term gets arrow 0, because 0 times everything on that term is equal to 0, and my formula now becomes D equals VIT. Okay, I'm almost done. I can now plug in the values that I have under horizontal. The horizontal velocity is 7.5 meters per second, and the time is 4.2 seconds. So I just have to multiply those. Calculator back out. I have 7.5 times 4.2 equals, and I get 31.5 meters. So I'll plug that in here as D equals 31.5 meters. And I am done, and I am happy.